The reef at night is never silent. Shells clatter faintly as crabs shuffle over the rubble, spines of sea urchins scrape against stone, and fish whisper through currents with fins that stir sand into glimmering clouds. Yet beneath this orchestra of life, there is a single hollow where silence reigns. In the dim crevice of a rock outcrop, barely larger than a clenched fist, a female octopus has chosen her last home. Her arms curl inward, not to strike, but to cradle. Clinging to the roof of her den is a shimmering constellation of eggs, each no larger than a grain of rice, translucent strings of pearls dangling like tiny lanterns. She hovers beneath them, drawing water over their fragile bodies, fanning them with a rhythm so steady that even the passing tide cannot break it. Predators move nearby, crabs, fish, and even other octopuses, but she does not stir to chase them. The hunt is finished. From the moment she laid her clutch, the countdown to her death began. What unfolds here is one of nature's most haunting paradoxes. A supreme predator, among the most intelligent invertebrates ever to live, is programmed to lay down its own life the moment its offspring appear. The mechanism that drives this is hidden in a gland no larger than a seed, lodged between the eyes. The optic gland, often compared to the mammalian pituitary, governs far more than reproduction. Before spawning, it secretes hormones that maintain a balance of appetite, exploration, and survival drive. But once eggs are laid, the gland flips like a switch. Its chemistry changes, flooding the body with signals that erase hunger, suppress hunting instincts, and replace them with compulsions for one task only: guarding, cleaning, and aerating the developing brood. The mother octopus will never eat again. She will remain in her den, fanning tirelessly, until exhaustion and starvation collapse her body. To watch her is to witness an ancient genetic script playing out, one that has survived unchanged for millions of years. Scientists who dissected females at different stages of brooding discovered that the optic gland was not merely turning off feeding, it was rewriting behavior at every level. The hormones it releases alter metabolism, shifting the body from growth and repair toward breakdown. Muscles waste away, skin loses color, and eyes that once tracked prey with precise calculation now remain fixed on the swaying veil of eggs. In evolutionary terms, this sacrifice ensures that the young receive undivided care in the critical weeks before hatching. Yet it comes with a chilling cost. Once the process begins, there is no return. The irony is that the same creature who now starves willingly was once among the ocean's most inventive killers. In her prime, she hunted with a technique as theatrical as it is efficient, the parachute pounce. Silently, she would drift over a rocky hollow, spreading her 8 arms wide like the canopy of a living net. With a sudden plunge, the arms collapsed over the rocks, suckers sealing every exit. Each sucker is not merely a suction cup, but a sensor, able to taste chemicals and feel textures simultaneously. Through cracks no thicker than a pencil, she could identify whether a crab cowered inside or if only empty shells lay beneath. In an instant, she would thread an arm through the opening, tasting her way to the target, coiling it inward with irresistible strength. What makes this method extraordinary is that it turns terrain into a trap. Where fish might dart or crabs scuttle to safety, the octopus transforms the entire landscape into a prison with a single gesture. And yet, when reproduction begins, that brilliance is silenced. The hunter becomes the caretaker, arms no longer weaving nets of death, but brushing debris from fragile shells. Her weapons are transformed into instruments of devotion. Even food crawling inches from her den will be ignored. Starvation is not gradual hesitation, it is enforced by chemistry. The optic gland's hormone flood ensures that her brain interprets hunger signals differently. Prey no longer excites. The urge to strike is muted. Only the rhythm of fanning remains. But the life of an octopus is never without shadow. Though she denies herself food for her young, octopuses are not strangers to cannibalism. Mating itself is a precarious dance, often ending with one partner devoured. In crowded dens where food runs scarce, larger individuals sometimes turn on smaller ones, dismembering their kin with the same precision used on crustaceans. Even mothers, weakened by fasting, have been known to consume a few of their own eggs if stressed or disturbed. It is an uncomfortable truth for those who romanticize these creatures as symbols of maternal sacrifice. Nature makes no promises of purity, only of survival, whichever path it demands. Beyond their dens, octopuses reveal a different side of intelligence, the capacity to manipulate objects for purpose. Divers in the Indo-Pacific have recorded them gathering coconut shells and assembling them into makeshift shelters, carrying them across sandy plains as mobile armor. In rocky habitats, they wedge stones and shells into the mouths of their dens, not simply as decoration but as barricades against intruders. To an untrained eye, these acts might appear whimsical, a curiosity of animal play. But the motive is rarely innocent. Many times, a barricade conceals a live prisoner, a crab or lobster trapped within reach, held like stored meat until the octopus decides to feed. This is not tool use as experiment, but as strategy, turning the environment itself into an extension of predation. It is this capacity for manipulation, deception, and learning that sparks heated debates among scientists and ethicists today. As global demand for seafood rises, proposals for octopus farming have emerged, aiming to cultivate them in controlled tanks as a new protein source. The logic is simple. Octopuses grow quickly, convert feed efficiently, and fetch high prices in markets from Spain to Japan. Yet the idea has drawn outrage unlike almost any other aquaculture initiative. The reason is not economic, but moral. Octopuses are solitary, curious, and demonstrably intelligent. They solve puzzles, escape enclosures, and show individual personalities. To confine such creatures in sterile tanks, deprived of the ability to explore, hunt, and build, raises ethical alarms. Unlike fish that shoal naturally, octopuses housed together often attack each other, tearing limbs and sometimes killing outright. Farming them at scale would mean confining predators who are asocial by nature, forcing lives of stress and likely suffering. Critics argue that the very traits that make octopuses desirable for human consumption, their intelligence, their sensitivity, their uniqueness, are the very traits that should exempt them from being farmed. They are the first invertebrates to be recognized under animal welfare laws in several countries, acknowledged as sentient beings capable of pain and experience. To industrialize their lives for food production, many believe, would not only be inhumane, but also a betrayal of our growing recognition that intelligence and awareness exist far beyond the human lineage. Back in the reef crevice, none of these debates matter to the mother octopus. Her body is already fading, skin mottled with patches where pigment no longer responds, eyes clouded at the edges. The eggs she guards are nearly ready. Inside each translucent capsule, tiny replicas squirm, miniature octopuses with arms already coiled, chromatophores primed to flash. At the final moment, the mother stirs for one last effort, flushing water through her siphon to propel the young outward into the open sea. They scatter instantly, each no larger than a fingernail, already orphans in a world that will claim most of them before dawn. For the mother, her task complete, collapse comes swiftly. Her body drifts from the den, no longer a predator, no longer a guardian, only the husk of one of evolution's strangest bargains. What remains is not tragedy, but design. The optic gland's fatal switch ensures that no mother abandons her brood early, no matter the hunger clawing at her. It ensures that even the brightest and most cunning hunter submits to a greater pattern of survival. In this cycle, self-sacrifice is not failure, but fulfillment, the passing of one life so that hundreds may have a chance. In the dark architecture of the ocean, where every creature is both hunter and hunted, the story of the octopus mother endures as one of the most profound. It is a reminder that even genius has limits, and that intelligence does not free a creature from the ancient scripts written into its blood. The sea is a mirror fractured by spray. Out beyond the surf line, a line of black and white bodies arcs in unison, vanishing beneath a steel-blue swell and reappearing in glittering bursts of foam. Each leap is a perfect parabola, water trailing from feathers like liquid diamonds. To an aerial view, they seem like a string of skipping stones flung by some giant hand, porpoising toward shore with the urgency of duty. One bird breaks from the line, lands with a slap onto the ice edge and shakes salt water from its plumage. Its crop is heavy with half-digested krill, carried miles from feeding grounds. Ahead stretches a landscape of shrieking voices, a city of feathers that sprawls across the ice in chaotic geometry. Within this colony, order is anything but gentle. Here the romance of penguins, their tuxedoed elegance, their clumsy waddles, fractures into something more unsettling. At the heart of the colony, where chicks cluster in ragged nurseries, danger is not always from predators. A returning parent threads through the mob, weaving toward the sound of its chick's call, a signature cry memorized since hatching. But as it nears, another adult lunges from the side, snapping with hooked beak at the downy bundle. Failed breeders, those who laid eggs that never hatched or whose offspring perished early, are known to attempt abduction. They seize chicks in desperate imitation of parenting, dragging them a few paces before being mobbed by furious neighbors. In many cases, the abducted chick does not survive the ordeal, killed not by hunger but by stress and injury from its own kind. This behavior shocks observers accustomed to the curated image of penguins as gentle guardians. Yet in the crowded architecture of a colony, where tens of thousands of birds press shoulder to shoulder, stress fractures the social fabric. Pecking orders form quickly. Dominant birds secure better territories with firmer ice and access to shade, while subordinates are pushed to exposed peripheries where chicks risk freezing winds or overheating in relentless sun. Disputes are settled with swift, brutal pecks, and blood often stains the snow. Survival in such a community is not just about endurance of cold or hunger, it is about navigating the violent politics of proximity. Beneath this theater of noise and aggression lies another phenomenon, invisible to the naked eye but no less extraordinary. The ground itself is saturated with guano, a pastel smear of green, pink and brown that cakes rocks and seeps into cracks. As it decomposes under sun and microbial action, the guano releases nitrous oxide, the same compound known as laughing gas. In penguin colonies large enough to rival cities, these emissions form plumes detectable meters above the ground. Scientists measuring the atmosphere above breeding sites report concentrations high enough to alter local air chemistry. What appears from a distance as a charming congregation of seabirds is, in chemical truth, a living reactor exhaling a greenhouse gas. It is a reminder that even beauty leaves a footprint, and that ecosystems are networks of invisible as well as visible exchanges. The pressure on these colonies is not confined to the air. Beneath the waterline, a deeper struggle is unfolding. Penguins are tethered to the movement of krill, shrimp-like crustaceans that bloom in vast belts along the edge of sea ice. When ice cover shrinks or shifts with warming seasons, the krill follow. The result is that parents must commute farther offshore, swimming tens of miles to secure enough food. Every extra mile means longer absences from the nest and chicks waiting longer with empty stomachs. In good years, when krill are abundant, the chicks grow fat and molt into waterproof plumage on schedule. In lean years, they wither before fledging, their deaths scattered silently across the colony like unpaid debts. The tragedy is compounded by competition from industrial krill fisheries, which harvest the same resource to feed aquaculture and produce supplements. To the penguin, whose life is a calculus of calories burned versus calories delivered, these shifts are not statistics, but the thin line between endurance and collapse. Underwater, the penguin is transformed. The wobbling comic figure on ice becomes a projectile honed by hydrodynamics. Its wings have become rigid flippers, bones flattened and joints locked, trading the gift of flight for something equally extraordinary, precision in a denser, colder medium. A stroke of the flipper generates a vortex, a swirling pocket of pressure that the next stroke grips, compounding thrust. At high speed, some penguins deploy a trick few creatures can match: bubble lubrication. By compressing air into their plumage near the surface and then releasing it as a shimmering sheath of bubbles, they reduce drag dramatically, accelerating in sudden bursts that rival torpedoes. Prey that seemed out of reach, schools of krill or silvery fish, are overtaken in an instant. What appears as playful streams of bubbles are, in truth, calculated physics, an energy-saving device that allows each dive to stretch its yield. Yet no matter how efficient the swimmer, life on land demands other adaptations. The Antarctic wind, armed with temperatures that plunge well below freezing, strips heat mercilessly from exposed skin. Chicks with their soft down are especially vulnerable. The solution evolved by penguins is collective rather than individual, the huddle. Groups of hundreds form dense, pulsating masses, bodies pressed so tightly together that the outer surface freezes while the core remains warm. Within the huddle, individuals slowly rotate, those who have endured the wind's edge slipping inward, those who rested in the middle pushing outward in turn. The pattern is not chaotic but emergent, a choreography that equalizes survival across the group. What seems a simple pile of birds is a solution drawn from physics, reducing surface area relative to volume, minimizing heat loss, and distributing costs across the collective. This balance between the individual struggle and the colony's mechanics is the central paradox of penguin life. Each bird must secure enough food to sustain itself, yet its survival often depends on synchrony with thousands of others. Each parent must defend its chick fiercely, yet be surrounded by neighbors that may injure or kill. Each colony emits gases that shape the very air above them, a reminder that even passive presence alters the planet's chemistry. And each journey to the feeding grounds recalibrates the energy ledger. Calories burned in flight like swimming weighed against calories brought back in the form of krill slurry to regurgitate into a chick's eager throat. Back at the ice edge, the parent that first leapt ashore locates its chick amid the chaos. The chick's peeping cry rises above the din, recognized among thousands like a fingerprint. The adult lowers its head, beak to beak, and a stream of half-digested krill flows from one mouth to the other. For a moment there is intimacy, a bond forged by recognition and trust. Yet only a few paces away, another chick cries out under the grip of an abductor, dragged awkwardly by the feathers as neighbors strike at the aggressor. Life in the colony is a spectrum. Devotion and violence, efficiency and waste, survival and death, all occurring within the span of a few square meters of ice. To step back is to see the colony not as a mass of endearing creatures, but as an ecosystem in miniature, a city that mirrors our own in its politics, pollution, and precarious resource chains. The penguin's life is measured in ledgers of energy, in equations of thermodynamics and hydrodynamics, in chemistry both above and below the sea. Its charm is not diminished by this truth. If anything, it is deepened. For behind the caricature of the waddling clown is a survivor shaped by forces as invisible as shifting krill belts and as vast as climate itself. The tuxedoed figure we so often laugh at carries within its stride the gravity of existence at the margins, where every flap, every dive, and every communal huddle is part of a lifelong negotiation with the elements. And so the parent, having fed its chick, turns again toward the sea. The next foraging run awaits, perhaps longer than the last, perhaps riskier. In its wake, the colony churns, a storm of feathers, guano clouds, and cries, a place where comedy and tragedy are indistinguishable. From a distance, it glitters like life itself condensed into black and white figures upon the ice. Up close, it tells a harsher truth. Survival is never cute. It is calculated, chemical, and costly. And the penguin, master of both sea and shore, balances this ledger every single day. The seafloor is a dim theater, its actors hidden in silt and shadow. Here, light fades to green-brown murk, stirred into clouds by every current. Few hunters would thrive in such blindness, but the walrus is not hindered. A massive body hovers above the bottom, skin mottled pink and brown, its head swinging side to side as whiskers rake the sediment like a comb through hair. Each vibrissa, one of several hundred thick, bristling whiskers, quivers with exquisite sensitivity, able to detect textures at the scale of microns. In total, the walrus carries an array so fine-tuned that even in water opaque with mud, it can map the shape of a buried clam or mussel as if reading braille across the ocean floor. The moment of discovery is subtle. The head stills, nostrils flare, and the jaws widen. What follows is not a bite, but a feat of physics. With a sudden contraction of tongue and throat, the walrus creates negative pressure so strong that a clam, nestled in the sand, is ripped upward intact. The suction is powerful enough to strip flesh from shell in one motion, leaving behind an empty husk on the bottom. It is engineering without tools, a mastery of hydraulics performed with nothing more than muscle and design. Unlike sea otters that hammer shells or gulls that drop them from height, the walrus is a surgeon of voids, its prey undone not by fracture, but by vacuum. This method is astonishingly efficient. A single adult walrus may consume thousands of clams in a single foraging bout, sifting across benthic plains that stretch for miles. The seafloor, once tranquil, is left stippled with pits, testimony to the scale of the harvest. These pits, however, do not vanish into emptiness. They become microhabitats where amphipods and worms settle, where fish larvae hide, reshaping the ecosystem in the wake of the walrus's feeding. It is a reminder that predators do not simply subtract, they also remodel, engineering landscapes through the very act of survival. But survival for the walrus is not confined to the depths. When it rises to breathe and haul out, the atmosphere of foraging gives way to one of danger. On an ice floe or a rocky beach, a herd may number in the thousands, bodies pressed tightly together in a living mass. From a distance, the sound carries first. Guttural bellows, snorts, and the splash of tusks striking hides. Yet beneath the chorus lies fragility. Among these giants weighing more than a ton, calves no larger than a Labrador dog huddle against mothers. In such density, panic is the predator. The trigger can be trivial, the shadow of a passing plane, the hum of a drone, even the snap of ice underfoot. In an instant, the herd surges. Hundreds of animals lurch toward the water, tusks stabbing, flippers thrashing, bodies crushing one another in the frenzy. Calves, too small to withstand the stampede, are often trampled or drowned. These tragedies have played out with increasing frequency as human activity presses closer to walrus resting grounds. Yet the solution, researchers note, is often simple. Observers who maintain hundreds of meters of distance reduce the risk dramatically. Respecting space can mean the difference between a herd settling calmly on the ice or a cascade of unnecessary deaths. The ice itself is central to the walrus's story. These animals are creatures of the margin, relying on sea ice not only as resting platforms between dives, but as strategic bases from which to access feeding grounds. Ice floes drift, carrying herds closer to benthic plains in summer and withdrawing them in winter. Migration patterns are less about geography than about ice geometry, tied to thickness, coverage, and stability. A shifting flow dictates where walruses can pause to feed and where they must travel further, expending energy with every stroke of their flippers. As the Arctic warms, the ledger tilts. Seasonal ice retreats earlier, leaving herds stranded on shorelines far from the shallow shelves where clams are abundant. Forced to swim longer distances, walruses spend more calories reaching prey, with mothers balancing the cost against the need to nurse calves. Winds play their part too. Stronger fetch across open water piles waves against coasts, breaking ice earlier and harder. Where once walruses hauled out on floating platforms that could drift near food, they now mass on beaches, sometimes tens of thousands strong, where disturbance risks escalate. The biology of the walrus is built for endurance, yet it is not limitless. Their skin, thick as armor, insulates against cold but bleeds heat quickly in warm weather, forcing them to sprawl with flippers raised, using vascular surfaces to shed excess warmth. Their tusks, iconic weapons that can grow over a meter in length, are not simply for combat but for leverage, hooking ice edges to haul up or gouging holes to access breathing space. Socially, tusks serve as markers of status. A clash between rivals is less about intent to kill than about performance, the display of size and will. The rhythm of these contests maintains hierarchy, a delicate balance that reduces conflict in the long term by making roles clear. Underwater, the walrus's foraging style contrasts with its lumbering bulk. Despite their size, they are agile divers, capable of submerging for more than 10 minutes at depths of over 80 meters. Each dive is a calculation, the oxygen stored in blood and muscle against the energy required to sift sediment and strip mollusks. Their metabolism slows during descent, heart rate dropping to conserve oxygen, while blood is shunted from non-essential tissues toward brain and heart. It is a strategy shared with seals and whales, but optimized here for a different prize. Not fish or squid, but bivalves embedded in mud. In this pursuit, calves learn by proximity. Mothers dive with their young trailing behind, whiskers twitching in mimicry, though their skill is years from refinement. Nursing continues long past the first year, a maternal bond that sustains calves until they can forage independently. Yet maternal devotion, powerful though it is, cannot always withstand the stampede. In crowded haulouts, mothers separated from calves often call for hours, their bellows echoing across the shore, unanswered. It is one of the crueler ironies of an animal built on tactile mastery, that on land, where sound and sight dominate, chaos strips them of the very bonds that define survival. And still, despite these vulnerabilities, walruses remain titans of adaptation. Their role in Arctic ecosystems is profound, consuming clams in such numbers that they shape benthic communities, fertilizing coasts with nutrient-rich carcasses when they die, and serving as prey for polar bears and occasionally killer whales. They are both predators and keystones, their presence rippling outward into webs of consequence. To see them in motion is to glimpse contradiction. One moment, an enormous male hovers underwater, whiskers sweeping sediment in a gesture as delicate as a pianist's hand. The next, that same creature barrels across ice with the momentum of a truck, sweeping calves aside in blind panic. They are engineers and hazards, sculptors of vacuum and victims of stampede. Their migrations trace the outline of a vanishing map, following ice that thins each year, rest stops crumbling beneath them. Back on the seafloor, the scene repeats. A swirl of whiskers, a sudden slurp, a clam stripped from its shell with clinical precision. Above, on land, a different drama waits. Thousands pressed shoulder to shoulder, the air heavy with musk and sound, vulnerable to the smallest disturbance. Between these worlds, the walrus survives, not through elegance or efficiency alone, but through a balance of power and fragility. It is a reminder that even giants live by rules set not by their strength, but by the physics of suction, the chemistry of ice, and the biology of fear. Nightfall in the tropics brings a transformation as profound as the switch of seasons. The reef, brilliant and bustling under daylight, sinks into chiaroscuro. Corals fold their polyps inward, parrotfish retreat into mucus cocoons, and the shadows deepen between the rock ledges that form the reef's skeleton. It is here in the narrow fractures and dark apertures that one of the ocean's most alien predators prepares to strike. The moray eel, its long body coiled like a spring, waits in silence. Only the faint undulation of its mouth betrays life, jaws opening and closing in slow rhythm, not a threat display, but the eel's way of ventilating gills. A fish drifts past the opening. The eel detonates forward, its head emerging in a blur, and then, in a moment that belongs more to science fiction than to natural history, a second set of jaws erupts from deep within its throat. These pharyngeal jaws surge outward, clamp the prey, and haul it back with conveyor belt certainty. There is no escape. This inner jaw is not merely a curiosity, but an engineering solution to a very real constraint. Morays hunt within tight crevices where there is no room to maneuver. Other predators rely on suction feeding, expanding their mouths to pull prey inward with water pressure. But the elongated skull of a moray leaves little space for the buccal expansion required for suction. Evolution has written a workaround, a set of pharyngeal jaws mounted on muscular slings at the back of the throat. When a fish is seized by the primary jaws, the pharyngeal jaws protract forward, independent of the skull, gripping and pulling the prey deeper. What this achieves is a transfer system, an escalator of flesh, that allows the eel to feed in narrow tunnels, where turning around would be impossible. The moray is not alone in having pharyngeal jaws. Many fishes possess them in some form. But only in morays are they mobile, protrusible, and functionally predatory. It is a design so startling that it reshaped scientists' understanding of vertebrate feeding when first filmed in action. Hunting for the moray begins not with sight, but with scent. Their eyes, small and underdeveloped, are poor instruments in the darkness of a reef at midnight. Instead, They rely on olfaction of remarkable sensitivity. Nostrils at the tip of their snouts draw in water, passing it over chemoreceptive tissues that can detect faint molecular trails. A fish injured yards away, a crustacean shedding its shell, or even the chemical residue of mucus along a rock face, all leave signals perceptible to a moray. In a way, they smell in stone, their awareness extending into fractures and hollows where sight cannot penetrate. For this reason, L-shaped or T-shaped crevices become hunting grounds of choice. They trap scents and funnel currents, creating chemical corridors that eels patrol with precision. Where a human eye sees only blank rock, a moray interprets invisible trails mapped in molecules. The ambush, when it comes, is not reckless. A moray lunges only when calculation suggests certainty. Its body, capable of knotting and reversing direction within seconds, allows it to anchor deep in rock while projecting only the head. This positioning ensures that once prey is seized, leverage favors the eel. Victims dragged backward into the crevice are not merely subdued, they are entombed, pressed against stone walls with nowhere to flee. The pharyngeal jaws then ratchet the meal inward, a grisly mechanical process hidden from outside view. Yet the moray's relationship with humans has grown complicated. In many tropical destinations, divers have sought to make these secretive predators more visible by coaxing them from dens with hand-fed fish. The practice may look harmless, even enchanting, an eel winding from the rocks, mouth agape, to take food directly from a diver's hand. But conditioning wild predators to associate hands with feeding is a dangerous equation. Morays with poor vision and hair-trigger bite reflexes cannot distinguish between a proffered fish and fingers. Serious bite incidents have occurred, some leaving divers with lacerated arms and missing digits. For the eel, such encounters can also prove deadly as conditioned individuals approach humans too readily, risking retaliation. The safe distance alternative, observing them naturally as they prowl or allowing them to hunt unaided, is not only safer, but more revealing. To see the moray in its own rhythm, unprovoked and unbaited, is to understand the elegance of its design rather than distort it into spectacle. Perhaps most remarkable is that morays are not always solitary hunters. In certain reef systems, they form cooperative alliances with groupers, robust, open-water predators that patrol the reef edge. A grouper in search of hidden prey will approach a moray's crevice and perform a distinctive headshake, a signal that recruits the eel. The moray responds by plunging into the labyrinth of rock, flushing fish from hollows into the open where the grouper can pounce. Sometimes the fleeing fish attempts to evade the grouper by darting back into crevices, only to be seized by the waiting moray. Success rates in such collaborations are significantly higher than in solo hunts. This interspecies alliance, based on signals and complementary skills, is one of the few known examples of cooperative hunting between fish species. It suggests a level of behavioral plasticity and communication far beyond simple instinct. The moray itself is a creature of contradictions. Its elongated body and perpetual gape make it appear menacing, but its aggression is largely defensive when approached without care. Its reputation as a rogue attacker is inflated by encounters born of hand-feeding or careless provocation. In truth, the eel is a patient specialist, sculpted by evolutionary constraints into a predator unlike any other. Its physiology is inseparable from its environment. Narrow skulls for narrow crevices, jaws within jaws for prey retrieval, chemical detection for darkened labyrinths. It is not simply an animal living within the reef. It is an extension of the reef's architecture, a hunter inseparable from the stone corridors it inhabits. Even the moray's skin tells a story of adaptation. Unlike many fishes, it lacks scales, its surface sheathed instead in a mucus coating that resists abrasion as it slides against coral. The mucus also carries antimicrobial properties, reducing infection risk from constant contact with rough surfaces. Its coloration, mottled and cryptic, blends with the reef, but many species also display striking patterns, tiger stripes, leopard spots, or jade green marbling, that render them iconic in diver lore. These patterns, however, are not for our eyes. They are camouflage tailored to the play of light and shadow within rock fissures, where dappled darkness masks their form. At night, As plankton blooms rise and the reef becomes a feeding frenzy of hunters and hunted, the moray slips silently through cracks, its body undulating in a sinuous crawl. Every movement is economical, every strike measured. To witness the pharyngeal jaws in action is to glimpse an evolutionary marvel, an independent feeding apparatus so efficient that it has persisted for tens of millions of years virtually unchanged. It is grotesque, alien, and yet perfectly logical. What emerges when all is said and shown is a portrait not of monstrosity, but of specialization. The moray eel's jaws within jaws are not an excess of horror, but an economy of design, a response to a life spent in stone corridors where suction is impossible and vision unreliable. Its cooperative ventures with groupers demonstrate that intelligence in the ocean is not the sole property of mammals or cephalopods, but can emerge even in the most unlikely partnerships. And its fraught interactions with humans serve as a reminder that our desire for spectacle often collides with the logic of survival. In the end, the moray eel remains one of the reef's most unforgettable enigmas, a predator whose menace masks mastery, whose grotesque second mouth is less monstrosity than necessity. Beneath the waves, in the silence of a midnight wall, the eel waits. Not as a nightmare intruder, but as the perfect answer to the puzzle of hunting in stone. The morning light spreads thin across the reef, slipping between spires of staghorn coral and settling over a giant that should not exist in such delicate surroundings. From a distance, it looks almost like a misplaced boulder, drifting slowly across the reefscape, massive forehead jutting like a cliff face, scales glimmering in shifting shades of green, turquoise, and indigo. Up close, the humphead wrasser, or Napoleon fish as it is often called, reveals itself as a leviathan of subtropical shallows. Stretching more than 2 meters in length and weighing well over 100 kilograms, it is a creature that moves with improbable grace. The reef's smaller inhabitants scatter before its passage. This fish is not only immense in size, but immense in role, a guardian and disruptor woven into the reef's fragile balance. The wrasser's legend begins with its jaws. They are not delicate instruments, but battering rams sheathed in fleshy lips. Watch one approach a clam wedged in the reef. The head tilts, the thick lips seal, and then, with a motion more violent than elegant, the fish hammers the shell against a hard coral or rock surface. Again and again, the sound resonates like stone on stone until cracks splinter across the shell. With a final crunch, the jaw muscles, capable of exerting thousands of newtons of pressure, finish the job. The clam is swallowed whole, shell shards and all. Few predators can manage such prey without risk, but the wrasser's gullet is lined for the task, its pharyngeal teeth grinding shell and flesh into digestible fragments. Yet clams are only one chapter in the wrasser's diet. The true spectacle arrives when it encounters a crown-of-thorns starfish. These echinoderms, bristling with venomous spines and notorious for devouring live coral polyps, are among the reef's greatest threats. Entire coral gardens can be leveled when outbreaks surge. Most predators avoid the crown of thorns, its spines pierce and its toxins inflame. But the humphead wrasser does not hesitate. With deliberate bites, it chews the starfish, spines snapping audibly between jaws. The toxins, lethal to many creatures, are rendered harmless by its digestive adaptations. In this gruesome feast lies salvation for the reef. The wrasser is one of the few natural checks on crown-of-thorns populations, a single predator capable of turning a plague into a meal. Without it, outbreaks swell unchecked, leaving skeletal wastelands where coral once flourished. This ecological role underscores a truth often missed when the wrasser is reduced to its spectacle. It is not simply another reef giant, but an architect of stability. By feeding on coral predators, from starfish to mollusks, and even destructive sea urchins, it maintains the balance that allows corals to persist. Remove the wrasse, and the reef becomes vulnerable to collapse. This is not hyperbole. In regions where humphead wrasser have been fished out, crown-of-thorns infestations have risen sharply, leaving scars visible even from space. The wrasser's strength is not only in its size, but in its influence. Its biology, however, is even stranger than its diet. The Napoleon fish is a protogynous hermaphrodite, meaning individuals begin life as females and later, under certain conditions, transform into males. Small females populate the reef in abundance, but as they age and grow, some undergo the shift. Ovaries regress, testes develop, colors intensify, and the characteristic hump enlarges. This transformation ensures that a few dominant males preside over harems of females, monopolizing spawning events that occur in large groups along reef slopes. The system works so long as those big males remain. Remove them and the structure collapses. Without mature males, females cannot reproduce effectively, and the next generation fails to appear. It is an elegant but fragile arrangement, one that human exploitation has cracked wide open. The humphead wrasser has become a luxury commodity in live reef fish markets, particularly across parts of East and Southeast Asia, where a single large male can fetch astronomical prices. Fishers, aware of the demand, target the biggest individuals, the very ones essential for reproduction. The irony is brutal. By consuming the largest males, humans do not merely reduce the population by one, they cut off the reproductive future of dozens of females dependent on that male's presence. Fisheries collapses have followed predictably, the once abundant giants now reduced to critically endangered status. To meet demand, many fishers turn to methods that are as destructive as they are effective. Cyanide fishing, in which sodium cyanide is squirted into coral crevices, stuns wrasser long enough for capture without killing them outright. The fish can then be kept alive in tanks until they reach restaurants, where diners choose them from aquaria as if selecting ornaments. But the reef pays the price. Cyanide not only weakens or kills the captured fish, but also poisons corals, disrupting symbiotic algae and leaving patches of reef barren. The practice persists because of profit, yet it dismantles the very ecosystems upon which future catches depend. Amid this exploitation, glimmers of resistance emerge. In Palau, for instance, community enforcement backed by cultural values has proven effective. Traditional leaders, local fishers, and conservation groups work together to patrol reefs, ban destructive practices, and protect spawning aggregations. Enforcement is not only legal but social, with communities imposing taboos and fines on those who breach collective agreements. By integrating local stewardship with scientific knowledge, these efforts demonstrate that sustainable coexistence is possible. Where such models thrive, wrasser populations stabilize, reefs retain resilience, and the market demand shifts toward other, less destructive fisheries. Watching a Napoleon fish glide across the reef is to witness both majesty and fragility. Its scales shimmer with turquoise that shifts to emerald as the angle of light changes. Its eye, set within the massive forehead hump, swivels with intelligence, scanning corals for hidden prey. Despite its bulk, it moves with slow elegance. Each beat of the pectoral fins a measured push against the water. And then, in an instant, power replaces grace. A clam is smashed, a starfish is crunched, and the reef is reminded that its guardian still patrols. But beneath the spectacle lies tension. Every large male that disappears to the luxury trade represents not just one loss, but the collapse of a social and reproductive system. Every starfish left uneaten in a wrasser-depleted reef represents a coral at risk. The jaws that can pulverize shells and spines are also the jaws that hold the reef's future. Conservation, in this light, is not merely about saving a species. It is about saving the foundation upon which entire marine ecosystems rest. The humphead wrasser is not invincible. It is slow to mature, living decades but reproducing late, making recovery from overfishing glacial. It is highly visible, its sheer size making it a target easy to spot and capture. And it is deeply enmeshed in cultures that prize rarity and extravagance. Yet in its biology lies resilience, the ability to change sex, the power to regulate ecological imbalance, the longevity to persist if given the chance. At the scale of the reef, the Napoleon fish is more than a leviathan. It is a keystone, an arbiter between coral and predator, between balance and collapse. Its story is a lesson in interdependence, that even the mightiest fish depends on the smallest polyps, and that the fate of entire reefs may rest on the survival of a single species capable of swallowing a starfish whole. The tide has slipped into slack water, leaving the reef suspended in a lull of silence broken only by the clicks of shrimp and the occasional groan of parrotfish grinding coral. In this calm, a slender banded form slides across the substrate with a motion that is neither the jerking undulation of an eel nor the staccato pulses of a fish. It is serpentine, deliberate and eerily quiet. The sea snake, with alternating rings of black and white, glides with the economy of a predator that has mastered two worlds. It knots its body to lever into a narrow cave, tongue flicking against stone, and after a heartbeat of stillness, it emerges again with a struggling goby clamped in its jaws. The fish writhes once, then goes limp, struck not by brute force but by chemistry delivered with surgical precision. Sea snakes are a paradox of design, air-breathing reptiles that live almost entirely in the sea. They trace their lineage back to terrestrial snakes that once slithered through forests and grasslands, yet evolution has rewritten them for marine existence. Their tails are flattened into oar-like paddles that slice through water with efficiency. Their scales, once friction against soil, are smoothed and reduced, creating a skin that moves with minimal drag. Even their nostrils, once the portals of air, have valves that snap shut underwater, protecting lungs from intrusion. These adaptations allow them to inhabit coral reefs, estuaries, and open ocean alike, where they weave through habitats as hunters specialized for an aquatic stage. At the heart of their hunting strategy lies chemoreception. Like their terrestrial cousins, sea snakes wield forked tongues that collect chemical particles from their environment. Flicking rapidly, the tongue samples the water, transferring molecules to the Jacobson's organ in the roof of the mouth. This sensory map is so acute that a snake can track fish hidden under coral rubble or buried in sand. Chemical trails dispersed by currents and turbulence are read as pathways, guiding the predator to prey it cannot see. To a diver, this looks like random weaving, but to the snake, each flick of the tongue builds a mosaic of information invisible to human senses. The physiology that enables this lifestyle is equally remarkable. Sea snakes possess a single elongated lung that stretches nearly the length of their bodies. This lung serves multiple purposes. It stores air, functioning as a reservoir for dives that last up to 2 hours, and it acts as a buoyancy regulator, adjusting the animal's balance in the water column. By modulating the distribution of air within this lung, sea snakes can cruise horizontally without sinking or rising, a reptilian solution that mimics the swim bladder of fish. Complementing this, the skin itself contributes to respiration. Though limited, cutaneous gas exchange allows some carbon dioxide release and oxygen absorption, reducing the frequency of surfacing. Each breath at the surface is therefore not a desperate gasp, but a deliberate renewal, after which the snake vanishes again into the reef's labyrinth. The strike, when it comes, is not prolonged. Sea snakes are armed with some of the most potent venoms in the animal kingdom. Their venom is primarily neurotoxic, disrupting the transmission of signals across nerves and muscles. Prey struck by their fangs succumb almost instantly, paralysis spreading before escape is possible. Unlike constrictors, which rely on strength and time, sea snakes embody efficiency. A small goby or wrasser subdued in seconds reduces the risk of attracting competitors or alerting the reef to danger. For the snake, venom is not about excess, but about minimizing struggle, conserving energy in an ecosystem where every calorie must be balanced against the costs of survival. To humans, the reputation of sea snakes is darker than the reality. Their venom is capable of killing a person, yet bites are rare, and fatalities even rarer. The majority of incidents occur not during encounters with swimmers or divers, but with fishermen hauling trawler nets. Entangled, stressed, and unable to surface for air, snakes thrash defensively, sometimes delivering dry bites with little venom, or at worst, injecting doses intended for small fish rather than humans. Their fangs are short, designed to pierce thin fish scales rather than thick mammalian skin, and their default strategy when approached by divers is retreat, not aggression. The danger, therefore, lies not in their intent, but in the context of human activity that ensnares them. Despite this, sea snake envenomations remain medically challenging. Antivenoms exist but are limited in distribution, often region-specific, and not always effective across species. Misidentification compounds the problem. With more than 70 species of sea snakes, many nearly indistinguishable in the field, treatment is not always straightforward. Fishermen bitten in remote regions may be hours from a hospital, where doctors must act quickly without certainty of which species was involved. Myths also cloud the narrative. Some communities view them as uniformly aggressive, others as harmless. The truth, as always, lies in ecology. They are predators with weapons honed for fish, not for us. Conservation concerns for sea snakes often focus less on venom and more on habitat. Many species rely on coral reefs, mangroves, and seagrass beds, ecosystems already under siege from warming seas, pollution, and coastal development. Declining coral cover means fewer crevices for hunting and refuge. Industrial trawling not only captures them as bycatch, but also devastates the benthic environments where their prey live. Habitat protection, therefore, is not just about safeguarding snakes, but about preserving the ecosystems that sustain them. Changes in fishing gear, such as turtle excluder devices and bycatch reduction grids, can reduce snake mortality significantly, offering pragmatic solutions that align conservation with livelihoods. At night, the duality of the sea snake becomes most vivid. One moment it surfaces, a sleek head breaking the still water, nostrils flaring as air rushes into the lung. The next, it dives again, body ribboning into the dark, tongue flicking, venom ready. It is an air breather in a liquid world, a land-born lineage rewritten for the sea. Its role is quiet yet profound, regulating small fish populations, recycling energy through venom-driven predation, and serving as prey themselves for sharks and sea eagles. To watch a sea snake knot itself into a crevice, then emerge with a limp fish dangling from its jaws, is to witness an organism perfected by compromise. It breathes air, yet seldom leaves the sea. It carries venom lethal to humans, yet rarely poses real danger. It is feared where fear is misplaced, and overlooked where protection is most needed. Their survival, like so many marine creatures, hinges not on their biology alone, but on our capacity to balance exploitation with restraint. In the end, the sea snake is not a symbol of menace, but of adaptation. Its forked tongue translates currents into maps. Its single lung doubles as both engine and ballast. Its venom, devastating at the molecular level, is wielded not with malice, but with economy. It is a reminder that evolution does not always seek elegance. Sometimes it simply insists on function, no matter how strange the form may appear. And in the quiet hours of a reef night, as the banded body vanishes again into stone corridors, the truth is clear. This is an animal not to fear, but to understand. On a rubble-strewn patch of reef, the seafloor appears unremarkable. Broken coral branches lie scattered, encrusted with algae and silt, while small gobies hover nervously above their holes. Amid this chaos of fragments, one particular shape is not what it seems. It is motionless, mottled brown and grey, its outline jagged like the dead coral around it. Yet within this apparent stillness lies one of the fastest predatory strikes in the ocean. A small damselfish drifts too close. In less than the time it takes to blink, the seafloor erupts, an enormous mouth gapes, water surges inward, and the damselfish vanishes. The rock settles again, unchanged, as if nothing happened. Only the absence of the prey betrays that a stonefish was ever there. The stonefish's legend has long been dominated by its venomous spines, but the true mechanism of its kill lies not in poison, but in physics. The strike is an act of suction, powered by the rapid expansion of the buccal cavity. When the stonefish opens its jaws, muscles yank the floor of the mouth downward and the opercular flare outward, expanding volume at astonishing speed. Water and whatever unfortunate creature is caught in its path rushes inward in a torrent. The suction is so strong that prey are pulled in even if they react instantly, their attempted escape overrun by the velocity of fluid flow. Unlike predators that rely on teeth or pursuit, the stonefish kills by turning stillness into a vacuum weapon. Its spines, despite their notoriety, play no role in hunting. The spines are instead instruments of defense, honed against larger threats. Along the dorsal ridge, 13 stout spines stand buried beneath fleshy sheaths. Each spine is connected to venom glands loaded with a potent cocktail of proteins and enzymes. When a spine is depressed, say by the weight of a footstep, the sheath slides downward, exposing the sharp tip and forcing venom upward into the wound. For a fish or shark attempting to swallow a stonefish, the result is excruciating, often lethal. For a human walking barefoot in shallow tropical waters, the outcome is a medical emergency. Victims describe pain so intense it surpasses broken bones or childbirth, radiating through limbs and sometimes inducing systemic shock. Hospitals in coastal regions of the Indo-Pacific are accustomed to these cases, with antivenom often the only reprieve. The spines, then, are deterrents, ensuring that a predator's lesson is learned swiftly and permanently. Camouflage is the stonefish's first and most consistent weapon, and it is achieved through more than color alone. Their skin is rough, encrusted with wart-like protuberances that mimic coral rubble. This texture manipulates water flow at a microscopic level. Most fish bodies create a boundary layer, a thin film of moving water that betrays their shape to sensitive lateral lines of predators or prey. The stonefish's irregular surface disrupts this layer, cancelling the telltale microflows and blending its hydrodynamic profile into the background of rocks and debris. Stillness, therefore, is not passive. It is an active strategy of invisibility, a form of behavioral camouflage that depends on physics as much as pigment. By erasing the signals that normally define a body in water, the stonefish becomes, in essence, a hole in perception. This strategy allows stonefish to hunt without movement for hours, even days. Metabolism is slowed to a crawl, conserving energy until prey strays close. The strike itself, though explosive, lasts only milliseconds. Muscles that powered the suction relax immediately, the jaws snap shut, and the body resumes its stony masquerade. Unlike pursuit predators, which must expend energy in constant motion, the stonefish thrives on patience. It is a strategy that works precisely because reefs are busy highways of fish traffic. Inevitably, something will wander near enough to trigger the ambush. For all their lethality, stonefish are not invulnerable. Juveniles, lacking both size and fully developed venom, are preyed upon by larger fishes and rays. Even adults can fall victim to predators immune to their toxin, such as certain sharks or sea snakes. These rare predation events underscore an ecological truth: no adaptation is perfect. The stonefish's defenses make it formidable but not untouchable. Its survival depends on the balance between camouflage, venom, and the mathematics of encounter rates. Humans, however, face stonefish in contexts far removed from ecological balance. In shallow tidal flats and lagoons where stonefish bury themselves beneath sand, they are invisible hazards. Barefoot waders or fishermen hauling nets often step directly onto them. The venom delivered in these accidental encounters is among the most painful known, capable of causing tissue necrosis and, in untreated cases, even death. Yet despite their danger, stonefish do not seek confrontation. Every spine activation is triggered by pressure, not aggression. They are ambush hunters, not attackers. The danger they pose to humans is a byproduct of their camouflage, an evolutionary solution to predation that collides with our habits of wading and fishing in shallow water. What makes stonefish particularly fascinating is their duality. They are simultaneously among the ocean's most dangerous creatures to humans and among its most energy-efficient predators. Their existence reveals how evolution balances paradox. On the one hand, they embody patience, conserving energy and striking only when prey is assured. On the other, they wield chemical weapons of extraordinary potency, not for hunting, but for deterrence. Their identity as the world's deadliest fish is thus misleading. Deadliest in what sense? They rarely kill prey with venom, rarely attack unprovoked, and exist primarily as still, cryptic guardians of small territories. Their danger arises not from their behavior, but from our intersection with their environment. Stonefish are also participants in wider ecological dynamics. By consuming small reef fish, they regulate population densities, preventing blooms that might destabilize coral communities. Their presence ensures a form of top-down control, subtle but significant in ecosystems where balance depends on countless small interactions. They are not apex predators in the sense of sharks or groupers, but they are regulators, their ambushes thinning populations of fast-breeding species. In this sense, they contribute to reef resilience, even as their spines make them symbols of danger in human imagination. Underwater, to observe a stonefish directly is to challenge perception. Divers who know where to look often fail to notice them until movement reveals the deception. The experience is uncanny, to realize that the rock you hovered above has eyes, gills, and the capacity to strike in a blur. It is a reminder of how much of the reef is hidden in plain sight, its dramas unfolding in camouflage and microcurrents invisible to us. For the stonefish, survival has always depended on this invisibility, its very name derived from its uncanny resemblance to inanimate stone. In an era when reefs are under siege from climate change, pollution, and overfishing, the stonefish represents both resilience and vulnerability. Its camouflage may hide it from predators, but not from habitat destruction. Bleaching events that turn coral fields into barren plains leave stonefish exposed, their disguises less effective against uniform backdrops. Shallow waters once rich in rubble and coral become wastelands where invisibility is harder to maintain. Even the deadliest fish must obey the laws of ecology. Without habitat, there is no ambush, and without ambush, there is no survival. The story of the stonefish is one of contrasts. A predator that kills without venom, yet defends with toxins so potent they terrify humans. A fish that expends almost no energy, yet strikes faster than the eye can follow. A master of camouflage that can still be betrayed by the disappearance of its habitat. To understand it is to see beyond the caricature of the world's most dangerous fish, and into the physics, chemistry, and ecology that make it remarkable. On the rubble patch, the damselfish's absence has already been forgotten by the reef. A few grains of sand drift down, covering the faint depression left by suction. The stonefish, once again indistinguishable from its surroundings, waits. The reef continues to bustle around it, oblivious to the silent hunter that pretends to be a rock. And in that stillness, the paradox of its existence persists. A fish that survives by disappearing, whose deadliest trait is not its venom, but the perfection of being mistaken for nothing at all. A grouper patrols the reef edge with slow, deliberate beats of its fins, eyes scanning for a quick meal among the smaller fish that hover nervously in the current. It notices one, compact, seemingly sluggish, hovering near the sand. The predator lunges. But in the space of a heartbeat, the target doubles, then triples in size, ballooning into a spiny orb too large to swallow. The grouper halts mid-strike, jaws gaping uselessly. In a moment, the would-be prey is transformed from morsel to menace. The grouper veers away, and the puffer drifts, its spines erect, its body a floating fortress. This duality, fragile and lethal, comic and dangerous, is the essence of the pufferfish. At first glance, puffers appear unremarkable, small-bodied, slow swimmers with little of the grace of angelfish or the sleek velocity of tunas. Their bodies are compact, their mouths small, and their fins proportionally modest. In evolutionary terms, they are poorly equipped for speed, pursuit, or flight. Yet their defenses lie not in outrunning danger, but in outthinking it. Inflation, their most iconic adaptation, is a mechanical marvel. Specialized muscles and an elastic stomach allow them to gulp water, or, when out of water, air, expanding into spheres several times their normal diameter. Spines that normally lie flat against the body snap outward, turning pliable skin into a bristling barricade. The strategy works against gape-limited predators such as groupers, barracudas, and sharks, whose throats cannot accommodate the inflated mass. Some predators, having once gagged on an indigestible puffer, never attempt the mistake again. Learned avoidance spreads quickly across reef ecosystems. Puffers do not need to survive every encounter, only enough to reinforce the lesson. Inflation alone, however, is not their ultimate defense. Hidden within their tissues lies one of the deadliest natural toxins known, tetrodotoxin. Unlike venoms produced directly by animals, this compound originates from symbiotic bacteria, particularly species in the genus Vibrio, that colonize the puffer's skin and organs. Tetrodotoxin functions by blocking sodium channels in nerve and muscle membranes, preventing electrical signals from traveling. The result is paralysis so complete that even breathing halts. For a predator, ingesting a puffer can mean death within minutes. The potency is staggering. Milligrams are sufficient to kill a human. For the puffer, this chemical alliance means that even if a predator succeeds in swallowing it, the consequences are severe enough to deter future attempts by others. In effect, their reputation as toxic prey is amplified through ecological memory. Predators that survive the mistake become unwilling to repeat it. The dual system of defense, inflation and toxin, is evolution's layered insurance. Inflation buys time, startling predators and forcing them to release. Toxin ensures long-term deterrence, spreading avoidance behaviors across entire predator communities. Together, they elevate a small, slow fish into a formidable presence on reefs. This balance explains why puffers can afford to forage openly on invertebrates, algae, and small crustaceans, swimming without urgency in places where other fish are constantly alert. They live under an umbrella of deterrence, their vulnerability transformed into resilience. Yet the puffer's story does not end with defense. In certain species, males create some of the most elaborate constructions in the animal kingdom. On sandy seafloors of the Western Pacific, a male sets to work with relentless dedication. Using only his fins, he sculpts a vast geometric circle in the sand, up to 2 meters in diameter, 10 times the length of his body. He carves ridges radiating outward like spokes, alternating with furrows that create a mandala-like pattern. The work continues for days, even weeks, as currents threaten to erase sections and the male tirelessly repairs them. But this is no idle art. The ridges function as sediment sorters. Fine grains accumulate in the valleys, while coarser particles roll to the outer rim. At the center, the male carefully arranges shells and fragments, adding ornamental flair. The final product is a sand mandala so precise that it rivals human geometry. For females, the structure is more than decoration, it is a signal of fitness. A well-constructed circle demonstrates stamina, health, and persistence. The symmetry reveals genetic quality, while the fine sediments and shell placement create microhabitats that benefit egg survival. When a female approves, she enters the circle, and spawning occurs at the center. The male fertilizes the eggs, which he then guards, continuing to maintain the nest until the hatchlings emerge. Here, architecture becomes both advertisement and nursery, a link between aesthetic beauty and reproductive success. It is one of nature's rare moments where geometry becomes a currency of life. This behavior, discovered only in recent decades, reframes puffers not just as survivors but as artists of the reef. Their sand mandalas are ephemeral, currents erase them within days if abandoned, but they represent one of the most complex courtship displays in fishes. In evolutionary terms, they are costly signals. Only the strongest, healthiest males can invest so much effort in a structure that confers no direct survival advantage. Like a peacock's tail or a bird of paradise's dance, the mandala is extravagance as proof of fitness. Humans, however, view puffers through a very different lens, as a delicacy. In Japan, certain species are prepared as fugu, a dish renowned as much for its danger as its taste. Only licensed chefs may prepare it, trained for years to remove the toxic organs without contaminating the flesh. When prepared correctly, fugu is considered a culinary art, prized for its delicate texture and the subtle thrill of its reputation. Yet accidents occur, and deaths from improper preparation, though rare, continue to haunt its image. Beyond legitimate cuisine lies a darker economy, black market sales of puffer meat and intentional poisonings. The very toxin that wards off predators has been weaponized by humans, sometimes as a means of homicide, other times as an illicit challenge. The fish's biology thus intersects with human culture in ways that blend reverence and recklessness. From an ecological perspective, puffers are not without consequence. Their grazing on invertebrates can shape reef dynamics, and their population fluctuations may influence prey abundance. In some areas, habitat change and overfishing of predators have allowed puffer populations to expand, altering local balances. In others, puffers themselves are harvested unsustainably for the luxury trade. Conservationists stress that their role as toxin carriers makes them difficult to farm safely, ensuring that wild populations remain the primary source. Protecting their habitats, therefore, is essential not only for the survival of the species, but for the preservation of reef balance. To watch a puffer drift across a reef is to see contrast embodied. One moment it is an almost comical balloon, puffed and spiny, bobbing awkwardly in the current. The next it is an artist, carving geometry into sand with patient dedication. Inside its tissues lurks a chemical that can silence nerves, while on its body lies a message of symmetry and beauty. It is a fish of contradictions, fragile yet lethal, awkward yet ingenious, deadly yet celebrated. Back on the reef, the grouper that recoiled from the inflated puffer circles away, wiser for the lesson. Somewhere on the sandy plain, a male labors over his mandala, finning furrows into perfect arcs, oblivious to predators driven by design. The puffer persists, not through speed or strength, but through strategies layered across chemistry, mechanics, and artistry. In its inflation we see survival, in its toxin we see deterrence, and in its sand circles we see the surprising beauty of evolution's extravagance. The horizon shimmers with an oily gloss, a slick line where two currents meet. Driftwood, seaweed, and the translucent bells of jellyfish collect along this invisible boundary, a conveyor belt of drifting life. From below, a green sea turtle rises into view, flippers pulling with slow but powerful strokes. Its beak opens, closing on the gelatinous dome of a jellyfish. Tentacles trail against leathery skin, harmless to the reptile that has evolved to endure their stings. The jelly collapses in a cloud of drifting tissue. Only meters away, another shape floats, pale, translucent, weightless. To the turtle's eye, it is almost indistinguishable. A plastic bag carried on the same current occupies the same lane as the jellyfish. The turtle veers toward it, oblivious to the difference. The feeding habits of green sea turtles are shaped by ocean physics. Convergence zones, lines where wind and current press flotsam together, create highways of opportunity. Jellyfish and other gelatinous organisms, easily carried by surface flow, accumulate here. For a turtle adapted to a diet rich in soft-bodied prey, these slicks are irresistible. Yet the same physical rules that concentrate prey also trap debris. Plastics discarded from coastal cities or drifting from rivers join the jellyfish in this floating buffet. The turtle's sensory systems, designed to cue on shape, translucence, and motion, are poorly equipped to distinguish one from the other. The result is a tragic overlap, a predator that cannot pass the difference between food and synthetic waste. This overlap has profound consequences. Ingested plastic clogs intestines, blocks nutrient absorption, or floats within the stomach, reducing buoyancy control. Some turtles become trapped at the surface, unable to dive, starving in plain sight of food they cannot reach. Others die slowly from internal perforations. To the human observer, a turtle nibbling at a plastic bag may appear almost comic, a mistake. But from the turtle's perspective, it is a rational act. It has learned across millions of years that translucent drifting shapes are calories. Evolution never anticipated polyethylene. The story grows darker when illness enters the frame. In many turtle populations, outbreaks of fibropapillomatosis, tumors that sprout across eyes, flippers, and internal organs, have become alarmingly common. These cauliflower-like growths can blind turtles, impede swimming, and weaken immunity. For years, the cause was a mystery. Recent research has revealed a viral component, but one that is exacerbated by environment. Poor water quality, particularly nutrient-rich effluent from sewage and agriculture, correlates strongly with outbreaks. In bays where seagrass meadows are bathed in nutrient runoff, algal blooms flourish, altering the chemical environment in ways that may weaken turtle immune systems and amplify viral transmission. The tumors, then, are not random afflictions, but symptoms of degraded habitats. They are biological indictments of how human pollution infiltrates even the bodies of animals we revere. The green sea turtle's life is already a saga of improbable navigation. Hatchlings emerge from nests dug into sandy beaches, scrambling toward surf with frantic flippers. Those that survive predators and surf drift into oceanic gyres, where they spend their early years feeding in the open sea. As they mature, many turtles transition to a more herbivorous diet, grazing on seagrass beds that they crop like underwater lawns. Yet the same individuals will travel thousands of kilometers across ocean basins to return to nesting beaches, guided not by sight or memory, but by magnetism. Evidence shows that turtles imprint on the geomagnetic signature of their natal beaches, the subtle variations in Earth's magnetic field that differ from place to place. This imprint acts like a map, stored in their nervous systems, allowing them to navigate years later with uncanny accuracy. A female that once hatched on a Caribbean island may cross entire basins to lay her own eggs on that same strand of sand. It is one of the most remarkable homing feats in the animal kingdom. Yet even this compass can be bent. Coastal construction, dredging, and shoreline reinforcement alter not only the landscape, but the subtle geomagnetic contours turtles rely on. Harbors lined with steel or artificial breakwaters distort the very field lines that guide them, introducing noise into the map. For an animal that depends on precision navigation, these distortions can be disorienting, diverting them from nesting sites and disrupting reproduction. This layering of threats, plastic mistaken for prey, tumors seeded by pollution, navigation scrambled by development, paints a sobering picture. Yet to see a green sea turtle in its element is to understand why survival persists despite such pressures. In clear water, it moves with a grace unmatched by its bulk. Each stroke of its flippers propels it meters forward with minimal effort, the body gliding as if suspended on rails. When grazing in seagrass meadows, its beak clips shoots cleanly, stimulating regrowth in a way that sustains the habitat itself. The meadows in turn act as carbon sinks, stabilizing sediments and storing greenhouse gases. In feeding, turtles engineer ecosystems, their appetites maintaining balance across seascapes that would otherwise unravel. The tension lies in the contrast between their ecological role and the hazards imposed upon them. They are architects of meadows, yet victims of sewage that seeps into those same meadows. They are navigators of ocean basins, yet undone by steel pilings on coasts. They are jellyfish predators, yet deceived by our discarded bags. Each example is less a failure of the turtle than of our own species, rewriting ocean rules faster than evolution can adapt. And still, the resilience of turtles is remarkable. Populations rebound when protections are enforced, when plastic waste is reduced, when effluent is treated, when nesting beaches are safeguarded. In regions where communities fence off nesting zones and regulate lighting, hatchling success soars. In marine protected areas, where seagrass is left intact and fishing is managed, adults return in greater numbers. The turtle's biology carries the capacity for long lives, sometimes exceeding 80 years. If given reprieve from human disruption, their life histories are long enough to rebuild generations. Back at the convergence line, the turtle surfaces for air, exhaling in a rush of bubbles before inhaling deeply. Its head dips again, eyes scanning the drifting slick. Jellies pulse, plastic sways, and the ancient predator follows instinct into a landscape transformed. For millions of years, these slicks meant food, navigation, and survival. Now they mean gamble. One meal may nourish, another may kill. In this moment, the turtle embodies the contradiction of modern oceans, an animal perfectly adapted to natural rhythms, navigating a world increasingly defined by human debris and chemical shadows. The green sea turtle's story is not just one of biology, but of intersection, between ancient instincts and modern disruptions, between geomagnetic maps and steel coastlines, between jellyfish and plastic. To watch one bite into a jellyfish is to glimpse evolution's precision. To watch one mouth a plastic bag is to glimpse our failure. Both images belong to the same truth. Survival in the Anthropocene is no longer written solely by predators and prey, currents and tides. It is written by us, and whether these turtles continue their migrations depends as much on our choices as on their instincts. The reef slope fades into blue, a threshold where coral outcrops surrender to the pelagic expanse. Here, Above a promontory swept by currents, the water churns with invisible signals, eddies rich in plankton, stations of service for giants. From the gloom, a silhouette appears, wings spanning 5 meters from tip to tip. A manta ray approaches, its cephalic lobes unfurling like twin scrolls, guiding water toward a cavernous mouth. With a slow, majestic roll, it glides through a column of cleaner wrasses that dart to its belly, nipping parasites from skin and gill slits. This is not merely hygiene, it is ritual. Cleaning stations anchor manta migrations as reliably as feeding grounds, places where wounds are healed and symbioses renewed. Yet within the same corridor, invisible in the deep blue, drifts a long line studded with hooks. The same path that mantas have followed for millennia has been co-opted by human extraction. The juxtaposition is stark. An animal evolved for grace and efficiency, navigating an ocean now laced with indiscriminate traps. The manta's angelic roll and the dangling hook share the same stage, and the contrast tells the story of beauty colliding with exploitation. The manta's feeding strategy is an exercise in fluid physics. Unlike whale sharks or basking sharks, which simply gulp vast volumes of water, mantas deploy a far more refined apparatus. Their cephalic lobes, flexible appendages on either side of the mouth, act as ducting veins. By curling and angling them, the ray channels incoming water into the oral cavity with precision. Inside, rows of gill rakers filter suspended plankton. The most remarkable feature is the ricochet separation mechanism. Rather than sieving particles like a sieve clogs, the manta's gill structures deflect plankton in bouncing trajectories, concentrating food without fouling the filter. This innovation allows mantas to feed for hours in nutrient-rich flows without pause, a system of elegance born of necessity. Clean flow is everything. Turbidity, plastic fibers, or excessive sediment can disrupt the delicate physics of ricochet, turning efficiency into futility. But evolution has equipped mantas poorly against exploitation. They reproduce slowly, reaching maturity only after a decade, with females producing a single pup every 2 to 5 years. This fecundity is among the lowest of any fish, a strategy built on longevity rather than abundance. In a stable environment, such pacing works. Adults survive long lives, populations remain steady, and calves inherit a safe world. In the face of modern fishing, however, the strategy collapses. Each individual lost represents not just a body removed, but decades of reproductive potential erased. It is biology stacked against resilience. The threat that looms largest is the trade in gill plates. In markets across Asia, manta gill rakers are dried and sold as ingredients in pseudo-medicinal remedies, touted, without scientific foundation, as cleansers of toxins or enhancers of vitality. Demand surged in recent decades, driving targeted fisheries that kill mantas for a single body part. For a creature with a lifetime reproductive output of only a handful of pups, such mortality is catastrophic. Local populations can crash within years, and because mantas migrate along predictable routes, entire aggregations can be emptied from known hotspots. The angels of the sea, as divers call them, are being traded piecemeal into extinction. Even when spared by fisheries, mantas face subtler assaults. Scientists examining stomach contents have found microplastics embedded among plankton remains. Fibers from textiles, fragments of packaging, and particles of degraded plastic infiltrate the same convergence zones where mantas feed. Unlike larger debris that turtles mistake for prey, these particles are inseparable from plankton swarms. Every gulp carries them inward, where they accumulate along gill rakers or pass into the digestive tract. The physiological consequences remain under study, but early findings point toward inflammation, reduced efficiency, and potential long-term harm. The irony is bitter. The same open ocean fronts that once guaranteed rich feeding now deliver a dose of invisible pollutants with every meal. The manta's vulnerability is heightened by its predictability. They gather at cleaning stations, returning year after year to the same reef outcrops. Divers know these places well, bommies or ledges where currents swirl and wrasses congregate. For ecotourism, this reliability is a gift. With regulated practices, keeping distance, avoiding flash, limiting boat numbers, manta tourism flourishes, delivering revenue to coastal communities while leaving the animals unharmed. Divers emerge awed, speaking of angelic encounters in cathedral-like blue water. The economic incentive shifts. A manta alive, gliding in circles above a reef, is worth infinitely more than a carcass stripped for gill plates. The success of such tourism rests on rules that respect manta behavior. Approach too closely, and the rays abandon cleaning stations, disrupting both hygiene and human experience. Allow them distance and they circle for hours, engaging in natural behaviors while divers watch from respectful margins. This balance demonstrates a broader truth. Conservation can succeed when human curiosity is harnessed responsibly, transforming exploitation into stewardship. In regions where manta sanctuaries have been declared, Indonesia, the Maldives, parts of Mexico, populations rebound, ecotourism thrives, and reefs benefit from the continued presence of these large filter feeders. The manta ray's story is therefore one of dual imagery. On one side they are angels, graceful giants sculpting fluid flows, engineers of elegance whose presence electrifies ecosystems and inspires reverence in those who see them. On the other, they are commodities, harvested for a set of gill plates, reduced to fragments of folk medicine, betrayed by their very predictability. Between these poles lies the decisive factor, our choices. To see a manta in motion is to glimpse what the ocean once was, an expanse where giants glide freely, nourished by currents untainted by microplastics, congregating at reefs where fish attended them without fear. To see a manta entangled in line or cut open for its gills is to glimpse what the ocean risks becoming. A wasteland of absence, where elegance is replaced by loss. Back on the cleaning station, the manta completes another role, wrasses darting to pick parasites from its gills. The current hums with plankton, and the animal's cephalic lobes unfurl to embrace the flow. Just meters away, a long line drifts, silent and waiting. The manta ignores it, for it has no concept of hooks or markets. It only knows currents, symbiosis, and the geometry of feeding. Whether its lineage persists for decades more depends not on its own strategies, refined across millions of years, but on whether we choose to allow those strategies to unfold in peace. The manta ray is both angel and omen, a symbol of what thrives when physics, biology, and ecology align, and a reminder of how quickly beauty collapses when exploitation intrudes. Its fate, like the clarity of the waters it filters, rests on the choices we make above the waves.